All right, so today we're going to be looking at properties of logarithms, and we're going to see different ways that we can manipulate them, or ways that we can kind of take shortcuts essentially to evaluate them and find more complicated solutions than just simply log base 2 of 4 is 2. Okay, but in order to do that, what we're going to do is we're going to look at some ones that we kind of already know. Okay, so just to recall and remind you guys. Because remember, exponentials and logarithms go hand in hand because they're inverses. Just to kind of remind you, if I'm doing the product of two powers, so if they have like bases but different exponents, if I multiply them together, right, then all I need to do is add the exponents, okay, and I keep the same base. The quotient of powers, right, is if I'm dividing like bases with possibly different exponents, right, what I do is I subtract their exponents. Okay, and whenever I have, like, if I'm taking a power to a power, so if I take, like, for example, 4 squared, I take that to the third power, right? I'm going to get it. That's when I multiply their exponents. Okay, so please keep those rules in mind and see, kind of like understand that when I multiply like bases, I add exponents. If I divide like bases, I subtract exponents. And if I take a base with a power to a power, I multiply. Okay. It's going to come in handy in a little bit. So the first one that we're going to talk about is called the product property of logarithms. Oh my goodness, my thing's not working at the moment. Hang on. There we go. All right. Come on. There we go. So we're going to look at the product property of logarithms. So in order to kind of see what's really going on, we're not going to prove these, but at any time if you want me to algebraically show you where these come from, you can feel free to ask, and I would not mind at all telling you. But we're going to kind of see how they, why they work as far as using real examples. So in problem number 1, if I look at log base 2 of 4, okay, what does that equal?
What is 2 to the what power equals 4?
Yep, 2 to the what power is 4?
2.
It's 2, right? It's 2. Okay, so log base 2 of 4 is 2, because remember, we're solving for, logs are about solving for exponents. Okay? Now what about log base 2 of 8? So again, the way that you want to think about it is 2 to what power is 8?
2 to the
Third. Okay. Now let's look at what happens if I multiply the inside. So if I take log base 2 of 8 times 4, right? That's the same thing as going log base 2 of 32. 8 times 4 is 32. What's log base 2 of 32?
5.
It's 5. Okay? It's 5. Kind of see what happened here, maybe? All right, so let's look at another example.
Because 2 plus 3
equals 5. Interesting, right? Now let's look at log base 10 of 10. What's log base 10 of 10? 1, right? Because 10 to the first power is 10. Okay? But what's log base 10 of 1,000? 3. Now if I think about the product of them, so log base 10 of 10 times 10,000 is log base 10 of 10,000, and 10 to the 4th will give me 10,000, so 4. So obviously by now we've probably seen what the pattern really is. Let's just look at one more for the sake of it. Okay? Log base 2 of 16 is what? 4. Log base 2 of 4, we already know, is 2. And then if I look at log base 2 of 16 times 4, log base 2 of 64 is 6. Okay? So if we're making a conjecture, if we look at log base 2 of 8 times 4, right, it's the same thing as log base 2 of 8 plus log base 2 of 4. Okay? If I look at log base 10 of 10 times 1,000, it's the same thing as log base 10 of 10 plus log base 10 of 1,000. And if I look at log base 2 of 16 times 4, it's the same thing as log base 2 of 16 plus log base 2 of 4. Okay? So this is what leads to what we call the product property of logarithms. Okay? If I have log base b of the product of two numbers, right, m and n, right, then it's the same thing as kind of breaking it up as log base b of m plus log base b of n. And you're probably going, well, what's the point of that? It'll make sense a little bit later, okay? Then how we utilize it. All right, we're not going to worry about this stuff down here. Okay. Now let's look at the quotient property. The quotient property of logarithms. So if you had to guess, right, based upon what happened with the product, what do you think is going to happen with logarithms when we're looking at their quotients?
The numbers will be smaller.
Numbers will be smaller, or
We're going to
you're going to subtract.
subtract instead of add.
Okay. So again, that's just kind of a cursory glance. That's kind of what we think is going to happen here. Let's look and see if that really happens. Okay. So problem number 1: log base 2 of 32 is what? 5. Okay. Log base 2 of 8 is 3. And if I look at log base 2 of 32 over 8, it's the same thing as log base 2 of 4, which log base 2 of 4 is 2. 2. What?
Log base 2. Oh.
Log base 2 of 4 is 2. Okay?
I was reading that backwards.
It's okay.
I was reading log base 4 of 2 for some reason. That's very different.
Yeah. Very, very different. Okay. All right. So then, so again, it looks like if I took 5 minus 3, I got 2. So far our theory is kind of proving right. Let's look at another one. If I do log base 10 of 10,000, what's log base 10 of 10,000? 4. Okay. What's log base 10 of 1,000? 3. And if I look at log base 10 of 10,000 over 1,000, right? 10,000 divided by 1,000 is 10. So log base 10 of 10, which we already know is 1. Okay? So far it's working. And just for posterity, log base 2 of 64 is 6. Log base 2 of 4 we already know is 2. And if I look at log base 2 of 64 over 4, it's the same thing as log base 2 of 16, which log base 2 of 16 is 4. And 6 minus 2 is 4. So based upon this, we know that if we're looking at log base 2 of 32 over 8, it's the same thing as log base 32 of log base 2 of 32 minus log base 2 of 8. Likewise for log base 10 of 10,000 divided by 1,000, and it ended up being the same thing as log base 10 of 10,000 minus log base 10 of 1,000. And log base 2 of 64 over 4 is the same thing as log base 2 of 64 minus log base 2 of 4. So very much like the product property, the quotient property says that if I take the quotient of two values, right, and if they have the same, if they're within the same log with the same base, right, then I can rewrite this as, so log base b of m over n, I can rewrite as log base b of m minus log base b of n. Okay, please know, right, very, very important. I keep doing that. Did that last time. That log base b of m over n does not, big huge, does not equal log base b of m over log base b of n. Please do not confuse the two. Okay. So if I do log base b of m divided by log base b of n, this does not equal log base b of m minus log base b of n, okay? That do not equal. No, okay? So, keep that in mind. And then our last property is the power property, okay? So, if we look at, for example, log base 2 of 4 cubed, okay? This is the same thing as log base 2 of 4 times 4 times 4, which, applying our product property, or power, according to the product property, not the power property, log base 2 of 4 times 4 times 4 is log base 2 of 4 plus log base 2 of 4 plus log base 2 of 4, okay? Now, log base 2 of 4 plus log base 2 of 4 plus log base 2 of 4, it's the same thing as if I do 2 plus 2 plus 2. It equals 3 times 2, because there's 3 sets of 2's added together. It works the exact same way. So this would be 3 times log base 2 of 4. Okay. For log base 10 of 10 to the 4th, then notice where the 3 was originally and where it ends up. Okay. So if I look at log base 10 of 10 to the 4th, this is the same thing as log base 10 of 10 times 10 times 10 times 10. Okay? Now, according to the product property of logarithms, I keep saying power, I apologize. Log base 10 of 10 times 10 times 10 times 10 is the same thing as log base 10 of 10 plus, log base 10 of 10 plus, log base 10 of 10. Which, again, very similar to the one before, right? There's 4 log base 10s added together. It's the same thing as 4 times log base 10 of 10. Okay? So, why is this important, right? Because this is just kind of a way for us to see, like, if I kind of look at what's inside of my logarithm, if I know what certain logarithms are, right, and then I come across one that maybe I don't know what it is, I can apply these properties in order to kind of actually come up with a real solution for this, right? And you'll see what I mean momentarily, okay? So if we're making a conjecture about the power of logarithm, or logarithm to a power, if I look at log base 2 of 4 to the 3rd, we found that it was 3 times log base 2 of 4. Log base 10 of 10 to the 4th was the same thing as 4 times 10 to the 10th. Sorry, 4 times log base 10 of 10. Long day. And so our power property of logarithms says that if I have some log base b of m and I take that to the nth power, right, it's the same thing as going, well, that's n times log base b of m's. Okay. So let's look at some examples of how we might use this, okay? So, if I know that log base 2 of 5 is 2.322, and I know that log base 2 of 3 is 1.585, and I know log base 2 of 30 is 4.907, then we can actually use those to find various other logs. Because again, you're probably going, well, how do we know that like a lot of these are true? So let's look at the first example. Log base 2 of 90, okay? You're probably going, oh, well, I can just type that into Desmos. And clear. Okay. Let's try it. So log base 2 of 90. So it's a simple logarithm. Just one. Log base 2 of 90. What happened?
Maybe if you tried to use the function instead.
Right, which function?
So if you go to function, and then it will say
Log.
log.
And then it automatically puts parentheses, right? And so this is the problem with calculators, okay? The problem with calculators is they can't do bases that aren't standard log, and we'll talk about that in a moment. So if I tried to use that for this problem, it's not going to work. So, but what I can do is I can rewrite this as log base 2 of 3 times 30. So I'm taking log base 2 of 90, and I'm rewriting it as log base 2 of 3 times 30. Okay? The reason why I want to do that is because I know log base 2 of 3, and I know log base 2 of 30. Applying the product property says that log base 2 of 30 is the same thing as log base 2 of 3 plus log base 2 of 30. Log base 2 of 3 times 30 is the same thing as log base 2 of 3 plus log base 2 of 30. Knowing that, we can substitute in the values that we do know, and we get that that's the same thing as 1.585 plus 4.907, which gives us 6.492. Okay? And that's the actual value of log base 2 of 90. And the same thing I can work for log base 2 of 25. Okay? I could write it as 5 times 5, or I could write it as log base 2 of 5 squared. Okay? Applying my power property, says that I can write log base 2 of 5 squared as 2 times log base 2 of 5. Once again, I know log base 2 of 5 is 2.322. So it's just 2 times 2.322, which is 4.644. Okay? So now here's what I want you guys to do. Okay? So please, if you haven't written it down or if you don't have this open, please remember what these three values are. Okay? You can go ahead and write them down now. And I'm going to put up the problems, and I'm going to give you guys a few minutes to work on those problems. And I want you to try and do them yourselves. If you have the document in front of you, you can just scroll down and start working on them.
Hey, dude, one thing I kind of don't understand.
Uh-huh.
Why don't they go directly from largest to smallest? So
What do you mean?
log 2 of 3 is about 1.6, just to be precise.
Okay.
Log 2 of 5 is greater. It's about 2.3.
Mm-hmm.
I don't even know what I was thinking. I was just,
Why didn't we write it as log base 2 of 30 times log base 2 of 3?
yeah.
Doesn't matter.
Okay. So you could break it into as many pieces as you want.
Absolutely. Absolutely.
Okay.
Yep. You can have a long chain of, like, for that one, 2, 3, 3, 5, 2. You can have a chain of 4 different logarithms, and you're still going to come up with the exact same answer.
I wonder.
All right, so here's the
On
problems.
the test, if it asks you to write down a logarithm or something.
No, it's going to ask you to evaluate, and some of them it will ask because it'll use variables instead of actual numerical values. So you just apply the properties.
Okay. But as you say, if you wrote it out as much as you could, like a chain like that on a test,
Mm-hmm. Yeah,
would you still get credit?
absolutely. Absolutely. But you're still
Maybe-
applying all the properties.
Maybe you could do an extra credit where it comes to who could make the longest chain on a test.
Mm-hmm.
You could do like a 20-point chain.
Yeah. Probably. I'm not going to, but I could.
And say, you know, where we do a chain, like find some number with a lot of factors and do a chain that goes from like the floor to the ceiling.
In college, I've done it. In college, I've done it.
Like, that's like a part of your actual homework.
Uh-huh.
Yeah, I'm not gonna major in math. Whatever.
Nah.
I
Math
know
was a fun
major
major.
would make you do that.
Math was a fun major. Like I said, I'm giving you guys a few minutes to work on problems number 1 through 6. Looks like we need another minute or so. Okay. All right, so I'd say we're just about ready. All right, so let's look at number 1. So log base 2 of 15. Who can give me a value of what you think this is? Was it?
4.51544993496.
I don't know how you got that, but unfortunately that is not correct.
Yeah, I don't know what I did.
3.907. All right, how'd you get that?
I did log 2 base 2 15, which would equal log base 2 5 times 3,
Perfect.
which would be log base 2 times 3 plus log base 2 times 5.
It's not times, it's log base 2 of.
Okay.
Or log base 2 of 5 plus
Plus log base 2 of 3.
log base 2 of 3. And log base 2 of 5 is?
2.322.
And log base 2 of 3 is?
1.585.
1.585. And when I add them together, I get 3.907. Perfect. Okay. What about for number 2? What do we come up with?
Log base 2 of 3 times log base 2 of 2.
Okay, times log base 2. So log base 2 of 3 times 2,
Yeah.
which equals log base 2 of 3 plus log base 2 of 2. What's log base 2 of 2? 1. And so we get 1.585 plus 1, which would give us 2.585. Okay? What's another way I could have done this? Another way I could have done this is I could have looked at this and gone, well, this is the same thing as log base 2 of 30 divided by 5, which is the same thing as log base 2 of 30 minus log base 2 of 5, which, no matter what, will still give you 2.585. Okay? So it doesn't matter. So there's lots of different ways that I could approach this and expand it and stuff. But either which way I use, I'm still going to end up with the same solution. Okay? So kind of save you guys from doing all these, or us looking through all these different ways that we could do these problems. I just kind of want to talk about solutions right now. So let's talk about what did we get for number 3. What did you guys come up with?
I got 3.322.
Perfect. 3.322. Because again, this is log base 2 of 5 times 2, or this is log base 2 of 30 divided by 3. Either way, it'll still get you it. Okay. What about log base 2 of 9? What do we get? 3.7?
17.
3.17, yep. 3.17, because this is log base 2 of 3 squared, or 2 times log base 2 of 3. What about number 5, log base 2 of 150?
7.229.
Perfect, 7.229.
Yeah.
And then lastly, log base 2 of 125, question number 6.
6.96.
6.966. Okay. And that's how we can do those if we already know what certain log values are. But like I showed before on our scientific calculator, right, we can't always calculate what some of these values are. So this stuff was great because I knew what those values were ahead of time. But what if we don't know them? Okay. So for example, if I want to look at, the bottom, if I want to look at log base 81 of 27, how in the world would I calculate this? It could be very, very hard. Now I could change this out and I could find a way to make this somehow out of like 81, and so like there's different ways that I could try it, but I would have to know what those values are. So wouldn't it be easier for me to just be able to type it in my calculator? Absolutely. So the problem with calculators and why they don't necessarily work is because logarithms themselves, there's an infinite number of possible bases as well as an infinite number of possible log bases of. So doing that, it's a lot of computation, tons of computation. And so that's why, like, if you think about it, calculators that would be able to calculate all different values of log, right, they'd be huge, they'd be massive. It takes so much memory, it takes so much RAM to be able to do something like that, okay? So instead, what they just use is, you know what, let's just make a standard log. Because computers usually talk in what's called binary, and so using just kind of one set thing will actually help us be able to work with those. And so the way that we kind of work around not being able to type in bases is what we call the change of base formula, okay? So there is a formula that says that, hey, if I have some log base b, log base b of some value m, I can always rewrite this as some log base c of m divided by log base c of b, of my base, okay? Now you're probably sitting there going, well, how does that help me be able to type it in my calculator? Okay? And you're probably also wondering, where in the world does C come from? The beautiful thing is C can be arbitrary. It can be any number that I choose. And this is still going to work. And this ratio is still going to be true. Okay? You're thinking about how, right?
So like if you like that in the calculator, like the base log, right? Like log base 10.
Okay, so that's exactly kind of what our point is. So in order for us, so why are we going to use C, and why do we care what that value is? Because I can change it to 10. So our goal here, is to have C equal 10. And the reason why is because if I think log base 10 of A, this is just equal to our standard log of A, which our calculator can actually calculate. Okay? This is our standard log. Okay? Because again, what we're trying to solve here is log base 81 of 27. What we're trying to figure out is, right, 81 to what power gives me 27? And that's very complicated. Okay? So, the way that I would use this change of base formula is I would say, okay, if I'm doing log base 81 of 27, all right, this is the same thing as log of 27, so standard log of 27 over standard log of 81. Okay? And that I can type into my calculator. So, let's see, clear? I'm going to type it in. So I'm going to go log of 27 divided by log of 81. And now I got my value, which ends up being 0.75, or exactly 3 over 4. So again, you're probably going, well, how did that turn out to be a perfect fraction? We'll talk about that in a second. So this ended up being 0.75, or 3 over 4. Well, why does that work? Well, let's think about it this way. What if I changed, instead of log base 10, what instead I did log base 3 of 27 over log base 3 of 81? 3 to what power is 27? 3. 3 to what power is 81? So it still works. Okay? It still works. Now, is it always going to turn out to be this nice and neat? Absolutely not. Absolutely not. It just does in this case because I wanted to use something that, well, it doesn't. It's something that we can actually use two different examples of different bases on. Okay? So doing it as log base 10 allows me to type it in my calculator, right? But if something's a little bit more apparent, if you notice that they're actually both can be written as exponents with like bases, then you can just do it that way if that's easier, okay? But it's not always going to be so obvious. All right. I was going to go through one example with you guys, but I would prefer you guys to work on the assignment right now. So I'm going to go ahead and stop the video there, and you guys can please work on the assignment. And I will be posting the video as well as this completed sheet in just a moment, okay? Yes.